Hi, my name is Joey Murphy. I'm a PhD student in the Department of Astronomy and Astrophysics at the University of California, Santa Cruz, where I work with Dr. Natalie Batalha. I study exoplanets, planets orbiting stars other than our sun. I'm interested in precisely characterizing the physical properties of exoplanets in order to better understand planet composition, formation, and ultimately to aid in the search for life outside of the solar system. I detect and characterize exoplanets orbiting other stars using both ground and space-based telescopes. These observatories include NASA's Transiting Exoplanet Survey Satellite, or TESS, which is in orbit around the Earth, and the Keck-1 telescope, which is located on the summit of Mauna Kea in Hawaii. TESS and Keck are complementary. They analyze starlight in different but synergistic ways. TESS produces time series photometry of stars. In other words, TESS measures the brightness of many stars across the night sky as a function of time. TESS is looking for special periodic dips in the brightness of stars that are indicative of an exoplanet. These dips, called transits, occur when an exoplanet passes between its host star and Earth, thereby casting a long-distance shadow and causing a decrease in the brightness of the star. TESS measures the shapes, sizes, and times of these transits. We can then use that information to determine the size and orbital properties of the exoplanet. Transits give us a lot of information about exoplanets, but we're still missing a key physical property: mass. To measure the mass of an exoplanet, we need to spread the light of the host star out into a rainbow in order to analyze it as a function of color or wavelength. This is called spectroscopy. The gravitational dance between a star and its exoplanet means that sometimes an exoplanet hosting star is moving toward Earth, and sometimes it's moving away from Earth. In other words, its radial velocity relative to Earth is oscillating back and forth. Using the Doppler effect, we can measure the magnitude of this oscillation by looking at the change in the wavelengths of the stellar absorption lines. Ground-based observatories like Keck have instruments that can measure the back and forth motion of absorption lines in stellar spectra and translate those measurements into a planet mass. Putting it all together, if we combine our transit and radial velocity observations, we can construct what's called an exoplanet mass radius diagram. This plot shows exoplanets, the colored markers, with planet mass on the x-axis and planet radius on the y-axis, where both quantities are relative to Earth. The color of the marker indicates the planet's temperature. The stars are planets that I myself have helped characterize. The plot also shows theoretical models of planet composition, which can be compared to observations. By continuing to populate this diagram with precise measurements, we're working to better understand the demographics of exoplanet composition and the physics of planet formation. These precise measurements are the critical first step in our search for life beyond the solar system. Thank you to ARCS for helping make this research possible.